Scientists at Bengaluru's Raman Research Institute have engineered the laboratory model receiver of PRATUSH, probing reionization of the universe using signal from hydrogen, a proposed cosmology experiment to study the formation of the first stars and galaxies. PRATUSH would orbit the moon and observe the sky at radio frequencies from the moon's far side, which is shielded from Earth's radio noise. In an engineering feat, the researchers have demonstrated that the entire receiver, with all its complexities, can be controlled with a simple Raspberry Pi, a common credit card sized single board computer, which has demonstrated the required sensitivity for the experiment. Currently, at the concept stage, PRATUSH aims for a 2-year mission once approved. In this context, we have with us today Dr. Mayuri S. Associate Professor at Raman Research Institute and Principal Investigator of PRATUSH. Hello, Dr. Rao. I am a Senior Journalist from ETV Bharat, Dr. Anubha Jain. Welcome to our channel, ma'am.
Thank you. Thank you so much for having me.
So first, we would like to know the concept behind PRATUSH and what makes it unique compared to other cosmology experiments.
Yeah, so PRATUSH aims to detect a very, very weak signal that comes to us from neutral hydrogen from the early universe. And specifically, what it will try to study is the formation of the very first generation of stars and galaxies in the universe. And this is an open problem. We don't know much about these first stars and galaxies, when and how they formed. And the challenge to doing this on Earth is that in addition to this being a very faint signal, we have a lot of radio noise on Earth. For example, our own FM stations have transmitters that transmit between 88 to 108 megahertz. So these numbers you hear after a FM band name, 94, 93, etc., they're the frequency of transmission in megahertz. And this is exactly the same band where we need to conduct this experiment. So the far side of the moon, so the side of the moon you do not see, is expected to be radio quiet because the moon blocks radio noise from the Earth. And also you have the advantage that you are in free space, so you have a clean environment, no radio noise from Earth, as well as no ionospheric disturbances. So PRATUSH is very unique in that sense that it will observe on the far side of the moon.
Okay, so what exactly is the 21 centimeter hydrogen signal and why is it important for studying the cosmic dawn and the epoch of reionization? And also I'd like to know how confident are you that PRATUSH can detect it?
Right. So the hydrogen atom, as many of us may know, is a very simple atom. It has a proton and an electron. Each proton and electron has a property called spin. So in an atom, the hydrogen atoms and the proton and electron spin can be in the same direction. They can be aligned or anti-aligned. So the anti-aligned state is the favorable state. So anytime a hydrogen atom's electron spin changes from being aligned to anti-aligned, it emits a photon, okay, basically light. And this light has a frequency of 1420 megahertz or a wavelength of 21 centimeter. So that is a 21 centimeter signal. So even the very earliest hydrogen in the universe, the primordial hydrogen that was formed when the universe was in its baby stages, that is the 21 centimeter signal we are trying to study today. So in cosmology, what happens is the wavelength gets stretched. So this 21 centimeter comes to us today at a wavelength of few meters or a frequency of about 100 megahertz. So we are trying to use the fingerprint of hydrogen and its evolution through the history of the universe to understand and interpret the stars that formed.
Okay.
As far as our confidence in detection, like in our paper, we have demonstrated that our laboratory model receiver has the sensitivity to detect the signal. So what this has to now translate to the space-based model, but purely from an environment perspective, the lunar far side, we are very confident that with this type of receiver sensitivity, we should be able to detect the signal.
Okay. So as you mentioned, the digital receiver or the small computer is credit card sized, so which has demonstrated the required sensitivity for the experiment. So how does this compact technology work and manage such sensitive measurements?
Yes. So the digital receiver right now is about the size of a small desktop PC, and this is the lab model. It'll get even smaller. That we're confident once we use the right sized electronics. But traditionally, we are so used as scientists to use such high-end computers, like our phone is a very fancy computer. But we cannot afford to fly such a fancy computer in space because the technology is not quite there. So for us, it was a challenge to demonstrate that a receiver this complex, which has to do all the right things, can be operated and controlled by a very simple, very popular computer used by people who do hobby electronics. It's called the Raspberry Pi. So we try to see if we can control our entire electronics using a Raspberry Pi, which is credit card sized, and we have been able to do so.
Okay. So, can you describe the role of field programmable gate array in processing cosmic signals and reducing noise?
Right. So FPGAs, as they are called, are like a chip, like you have chips in your phones and computers. This is a slightly more advanced version of chip that we can program. And it does, in our experiment, it does the function of actually taking the data, processing it, and generating the final measurement spectra, the thing that we actually want to observe. So taking the data as raw voltages, there is something that digitizes it, and the digitized signal gets converted to a spectrum. And that is then finally grabbed by our single board computer, by the Raspberry Pi.
Okay, right. So, if I talk about the challenges, so what were the main challenges in reducing noise to detect the weak hydrogen signals? And similarly, what challenges were faced in designing the antenna analog receiver for such low frequency signal? Or
Uh,
anything specific you like to mention regarding this?
Yeah, I mean, lots of challenges because it's a very challenging experiment. This signal that we're trying to go after has never been detected before. One group came close from the US, but that's not a confirmed detection.
Okay.
So, general challenges are the same. You have to design a very clean experiment. You have to operate it in a very clean environment, like the lunar far side in this case. And you have to make sure that you design, for example, the antenna cannot be designed in isolation of where it operates. In our case, Pratush being a space-based proposal, we had to co-design the antenna along with the satellite. And those it goes through a lot of iterations. And we have now finally arrived at a baseline design. And this we have to now translate to the space model.
Okay. So, why was the far side of the moon chosen as the observation side, not the Earth-based or orbit observatories?
Yeah, like I said, there are efforts underway on Earth as well, but the main three challenges that face experiments on Earth are radio frequency interference or noise from radio emissions on Earth.
Hmm.
Second is the ionosphere can create some confusing signals that come to our antenna. And the third is when you design and place such a sensitive experiment in any environment, for example, on soil, on a stone, on a table, the table properties, for example, can change your antenna properties because this is like a 1 part per million detection. So ideally, you want to be in free space. So
Hmm.
in the far side of the moon, in orbit, all these three problems are removed,
Okay.
and that makes the far side of the moon a good place.
Okay, right. So, Pratyush is still in the pre-project phase. So, what are the next steps, for the mission, and what milestones need to be achieved before launch?
Right. So, as far as the laboratory model itself, I think this is a fantastic milestone that we've been able to achieve.
Right.
We're now looking forward to various stages of reviews, working with ISRO on this. We also have some other technology demonstrations that we want to do on the ground-based experiment.
Hmm.
Once that is done, it will be left to the review process to determine what goes next and project mode. Yeah.
Okay. So, what are the main technical or scientific risks you foresee for Pratyush, and how do you plan to mitigate them?
Yeah. So there are two primary technical risks. That's what we are working on right now as an R&D problem. One is we can do all of these interesting laboratory developments with the sensitivity, but this entire experiment now has to fly and operate on the far side of the moon without our experiment itself being the source of radio noise. So we
Okay.
have to make sure that the noise that comes from our own electronics is suppressed to the correct levels, and we should be able to do this in a way that is space qualifiable. And the second is our antenna will see a lot of extreme temperatures almost 500 degrees Celsius of getting hot and cold. And that can change the antenna shape. And these are two major problems that we're working on addressing now. But we're confident that, talking to people with the right expertise and with our own R&D, we'll be able to solve this.
Okay, right. So, could this technology be used for future space or radio astronomy missions? And how does this mission show India's role in space science and cosmology?
Oh yeah, absolutely. For example, a lot of everything we're demonstrating is at par at the global level. We are competing neck to neck with counterparts from across the world who are trying to do the same thing. So we are at the kind of along with them on the front line, and
Mhm.
it bodes really well for Indian astronomy if we are able to go ahead and do this. It'll put us definitely on the global map.
Okay, right. So, how long is the proposed mission lifetime, and how will the data collection be structured over this period?
Yes, so we are expecting or we're hoping for a 2-year mission lifetime. What we would need is about 100 hours of extremely good quality data from the far side. But
Mhm.
because of the lunar orbit, we won't get this time continuously. We may get 5 minutes in one orbit, 45 minutes in another orbit. And this data will be buffered and downlinked back to ground stations when the satellite faces the Earth on the near side of the moon.
Okay. So, a different question I'd like to ask: if Pratyush is designed as a solo experiment with a dedicated spacecraft, could it operate alongside other lunar missions, or does it require full isolation?
Uh, yeah, so this is something we are investigating. The advantage of having a dedicated craft is, again, like I said, we are able to control the noise from electronics much better if we have our own instruments to worry about. If we are co-located with other experiments and instruments, we have to work with those teams to make sure that things are still radio quiet. But we are hoping that even though we may be a dedicated craft for going about the moon, the launch need not be a dedicated launch. So we could go along with other experiments and get injected into our own orbit.
Okay, right. So, are there any particular theoretical predictions or cosmological models that Pratyush aims to test or constrain?
Yes, so there is a whole family of models that theorists have predicted. So that is what we've kept in mind designing the experiment to have the necessary sensitivity. So what we call the more standard models, most of them Pratush should be able to constrain, which hopefully will tell us something about the first stars and galaxies.
Okay. So, in the end, like to know if Pratyush successfully detects the cosmic dawn signals, what would be the immediate impact on our understanding of the early universe?
So there are two main problems still remaining, what we call popularly the Big Bang model. One is something called inflation, which happens right after the birth of the universe. And the second is this problem we're talking about. So that is a major gap in our understanding of the evolution of the universe. So that we will effectively fit one of the largest missing pieces of the puzzle, and that will be a big milestone in cosmology and astrophysics.
Right, right. Thank you so much. And this was Dr. Rao, and thank you, madam, for this wonderful, insightful information. Thank you once again.
Thanks a lot.